Hi everyone, so today's topic is about dynamic programming and how you can learn dynamic programming that we are going to learn in this series, right? So I will start with a very famous quote about dynamic programming. This, those who cannot remember their past are condemned to repeat it, right? So I will explain what this quote means and what dynamic programming is all about. So we will talk about what is DP and where you can apply DP, and we will see few examples of dynamic programming in this video. Okay. So coming to the first question, let me start with a very simple example. Let's say I give you one problem. Let's say you need to compute this sum. Let's say 1 plus 1 plus 1 plus 1 plus 1. So I ask you, tell me what this sum is. So what you will do, you are just going to count the number of ones and you are going to say the sum is going to be 5. Now let me give you another problem, and let's say you need to count this. Okay. So now you will say this answer is going to be 6. So how do you compute this sum, right? So there are two ways. One way is, okay, this sum is 5 and I just need to add 1 to the previous sum to get 6. So what is this? So this is something that you have learned from the past, right? So this is what you have learned from past. Okay. So if you use this technique, if you remember what you have solved in past, you can easily optimize this problem, right? So other way would be, if you do a brute force, you will again spend a linear time in counting the number of ones. But if you know the answer to this sub problem, you can easily compute this problem in order 1 time, right? So this is what DP is all about. It is about remembering the problems that you have solved already, right? So this, for example, if I say this is a problem that you need to solve, right? And let me say, okay, this is a sub problem for this given problem, right? Okay. So what is DP? So DP is all about remembering the problems you have solved in the past, right? So it is, we need to memorize the solutions of sub problems that we have already solved, and where we can apply DP. Again, very important question, right? So in lot of problems, you can see there are certain algorithms, there are certain problems which follow a greedy approach, there are certain problems which follow a DNC approach, there are many problems which can be solved using dynamic programming, right? So DP is all about logical thinking, and let me give you the two cases where you need to apply DP, right? The first property is called optimal substructure, which means you can divide a problem into smaller instances of the same type. For example, if I say I need to compute a Fibonacci number, right? So yeah, let me also tell about the second property, which is called overlapping subproblems. Okay. So let me explain you these two properties, and if a problem contains these two properties, you can definitely apply dynamic programming to solve that kind of a problem. For example, in this case, let's say this is a function sum, right? And it gets some data and you get the answer as 6. So if this problem is to compute sum, this problem is also about computing the sum, right? So the smaller sub problem is of the same type. So you can say sum of 6 elements in the array can be expressed as sum of 5 elements of the array, these 5 plus 1 or plus array of 5, whatever it is. So you can see it follows a optimal substructure. You can express a bigger problem in terms of smaller subproblems. So this is a bigger problem, this is a smaller subproblem. So this property of expressing a bigger problem in terms of subproblem is called optimal substructure. So this is what the optimal substructure is all about. And it is not just DP where you will follow optimal substructure. You can have optimal substructure in other types of problems also. For example, in divide and conquer. A very good example of divide and conquer is merge sort, where you divide an array of size n into two different arrays of size n by 2, and you say, okay, I'm going to solve this subproblem, I'm going to sort this array, I'm going to sort this array, and then I'm going to combine these two to get my sorted array, right? So here you also have this property of optimal substructure, but what you will not have here is the property of overlapping subproblems, right? So let's see what does overlapping subproblem mean, right? Okay, let me take another example, that is of Fibonacci numbers, right? For example, you need to compute a particular Fibonacci. Let's say you need to compute fib of 5, and you also know that f of n is given as, okay, let's say you want to compute f of 5, and you also know f of n is given as f of n minus 1 plus f of n minus 2. So in order to do this, what you will do, you will say, okay, let me just, yeah, so let me say fib of 5. To compute fib of 5, I need fib of 4 and fib of 3. To compute fib of 4, I need fib of 3 and 2. To compute fib of 3, I need fib of 2 and fib of 1. And to get this, I again need 2 and 1, I need 1 and 0, I need 1 and 0, and I again need 1 and 0. So if you carefully look at this diagram, so you will find that there are many states, okay, there are many states in this which are getting computed multiple times. For example, have a look at this subproblem and this subproblem. These two are exactly same. If you look at this, this and this, these are also same, right? So if you look at this problem, it has both of these properties. It has optimal substructure, where you are breaking down this problem into smaller subproblems of same type. And second, you can see that, yeah, so you can see that these problems, right? So if you compute fib of 3 here, you can store the answer, and here you do not need to compute fib of 3 again. So here we are wasting time, right? So when you write a recursive solution, you can analyze the complexity of this becomes O of 2 raised to the power n, right? So we need to remember the subproblems so that we do not compute this entire subtree again, right? So this is what DP is all about. It will allow you to memorize the solution of a subproblem that you have already solved, right? So second property is the property of overlapping subproblems. Do not compute the same subproblem again and again, right? So this is what we are going to do. So I hope you got an intuition what is DP, where it can be used, and we saw one example of Fibonacci, right? So let's see if we solve this problem using dynamic programming, what changes we will make. For example, again you start from f of 5, and this time in order to store your answers you need some data structure like an array or a hash table. So let's maintain a hash table or an array which can store the answer for all the states. So let's say this is a DP array, and it is going to store the values I have computed so far, right? So let's say I want to compute fib of 5, I am going to make a call on 4, and later on I will make a call on 3, but first let's expand 4. So let's make a call on 3, let's make a call on 2, but let's first expand 3. Let's make a call on 2, and let's make a call on 1, and let's also make a call on 1, and let's make a call on 0, right? So these states, we will come to these states later on, right? So when you reach 1, you know this is the base case. You can return 1 from here, you can return 0 from here. So, and when you are going to return anything from a particular state, you are also going to mark the answer for that state as whatever the answer is, right? So at fib of 2, you know the answer is going to be 1 plus 0, which is 1. At fib of 1, you know the answer is going to be 1, right? And at fib of 3, right? So when you're going to return from 2, you can see that this particular state is not computed as of now, right? So you can mark, okay, the answer is going to be 1. So at 3, you will make a call on 2 and you will make a call on 1. So you get the answer as 1 plus 1, which is 2. Okay. from 4 you are making a call to, so this is 2. From 4 you are making a call on 3, which is computed now. You are making a call on 2, and now you can check in this table if fib of 2 is computed or not. So as you can see that fib of 2 is already computed, so you can just return 1 from here. And this becomes 3, so you store the answer as 3. And at fib of 5 you are going to make a call on 4, and from here you are going to make a call on 3, and you can see that 3 is already computed, so you just return what? Fib of 3, which is 2. So fib of 5 is now 3 plus 2, which is 5, and you store your answer here. So this is how you are going to apply DP, right? So there are two ways in which you can apply DP. So this approach that we just discussed is called top-down approach. Okay. So this approach is called a top-down approach. The other way that you could have done to solve this problem would have been a bottom-up approach, right? So top-down is nothing but recursion. You apply recursion plus you have a DP array which stores your answers of the sub-problems that you have solved. So this is called recursion plus memoization. Okay, so you are just doing recursion but with memoization of the states that you have solved these problems, so we will just remember the results of that sub-problems, right? So yeah, let's just quickly discuss about the bottom-up approach also. So for example, the bottom-up approach is very simple, right? So in this approach, you will start with the smallest sub-problem. Let's say this is 0 and this is 1. And you know that each box of this DP array can be computed by knowing the answers of previous two boxes. So you can clearly see that DP of I is nothing but sum of previous two states. So you can just see, so you can say, okay, for DP of 2 I need to sum these two values. So this is 1. To get DP of 3 I need to do 1 plus 1, which is 2. To get DP of 4 I need to sum these, which is 3. And to get DP of 5 I need to sum these, which is also 5, right? So this approach in which you are building your solution from bottom to top, you start from the smallest sub-problem and you go towards the biggest sub-problem, that is n. This approach is called a bottom-up approach, right? So I will just write it again. From smaller sub-problem you go towards a bigger problem, that is your DP of n. And in this case you start from the largest possible problem, which is DP of n, and you move towards the base case and you again build up your solution by coming from the base case towards the main case, right? So this is how top-down DP is, and this is what bottom-up DP is. In the next video, we will talk in more detail about these two types of dynamic programming along with the code. See you guys in the next part.